Let's talk about black holes and the Big Bang, the two biggest, baddest mysteries in all of cosmology. These are the places where our understanding of the universe just hits a brick wall. And that wall is called infinity. But what if that wall isn't really there? What if we could just find a way to erase it? Okay, so let's get right into it. For more than 100 years, Einstein's theory of general relativity has been our map to the cosmos. It's beautiful, it's powerful, and it works. Almost all the time. But here's the catch. In the two most extreme places you can imagine, deep inside a black hole and at the very beginning of the universe, the theory just breaks. It spits out an answer that physics can't compute: infinity. So, let's tackle that first cosmic headache, the one hiding right at the center of every single black hole. This is what we're calling Einstein's infinite problem. According to general relativity, when a giant star dies, all of its stuff gets crushed down into a point that is infinitely small and infinitely dense. It's called a singularity. And you should think of this like a cosmic blue screen of death. When physicists see an infinity in their equations, they don't think, oh, that's what reality is like. No way. They see it as a sign that the theory itself has crashed. It's a glitch in the very source code we're using to describe the universe. And this really gets to the heart of it all, right? The problem and a really cool potential solution. On one side, you have general relativity's dead end, infinite density, a place where physics just gives up. But on the other side, there's this new idea, the vacuum phase convergence theory, or VPCT, and it suggests something wild, that space-time itself physically pushes back, stopping the collapse before it hits infinity. It forms a core that has a finite density, a place where physics still works. So we go from a total breakdown to a potential breakthrough.
So how on earth is that even possible? How can space-time push back? Well, the answer comes from completely rethinking what space-time actually is.
We usually think of the vacuum of space as just nothing, right? Total emptiness. But this theory flips that completely on its head. It says the quantum vacuum is a real physical substance. It's a medium with actual properties like density and stiffness. So in this picture, space-time isn't just the empty stage where the universe acts out its drama. Space-time is the stage, the actors, the whole shebang. It's made of this stuff. Now, the theory gives this vacuum a kind of source code, describing it with a physical field, which you can see in this equation. Now, don't worry about the math, that's not the important part. The crucial takeaway is that this equation gives space-time a real, tangible structure. Just like a piece of steel has stiffness or water has a certain density, this theory says space-time itself has real, physical, mechanical properties. Okay, so if space-time is a physical thing, how does that change the story of a black hole? Let's dive in and see how this completely rewrites what happens in that extreme environment. So, as a star collapses, it's not just crushing matter, it's squeezing the very fabric of the vacuum. But here is the absolute key. You can't just squeeze it forever. According to this model, as the vacuum gets compressed, its stiffness actually goes up. Think of it like a trampoline. The harder you jump on it, the more it pushes back. Eventually, you hit a limit. The compression reaches a maximum physical point. The vacuum becomes saturated. And boom, instead of collapsing to infinity, it forms a stable core with a finite density. And the result is, well, there's no singularity. At the center of a black hole, there's this brand new thing, a core made of quantum vacuum condensate. It's a super stable region of space that's been squeezed down to its absolute physical limit, creating a whole new state of matter with a constant, incredibly high density. And the density we are talking about here is just staggering. The calculated maximum density is this number right here. It's so ridiculously huge, it's almost impossible to wrap your head around it. It's basically the famous Planck density. But what's the most important thing about this number? It's a number. It is not infinity. And in the world of physics, that makes all the difference. All right, so we've erased infinity from inside a black hole. That's a pretty huge deal. But if this idea really works, the implications get even bigger. This doesn't just change how we see black holes. It could change how we see the very beginning of everything. And this leads to a really fascinating question. I mean, if the infinite point inside a black hole is actually just the vacuum hitting its physical limit, then what about that other famous singularity? What about the Big Bang? And this is where the theory gets really, really elegant. You see, general relativity gives us two infinities, forcing us to have two separate broken explanations. But VPCT, it gives us one unified picture. It suggests that the core of a black hole and the state of the universe right at the Big Bang are basically the same thing, a saturated vacuum state, maxed out at Planck density. One single theory, one physical process solving two of the biggest mysteries in the cosmos. This completely reframes our entire origin story. The Big Bang wasn't some magical event that popped out of an impossible, infinitely dense point. Nope. It was a physical process, a phase transition. The universe might have started as this super compressed, highly ordered vacuum state that then relaxed, expanded, and cooled into the space-time we live in today. It's a physical beginning, not a mathematical error message. So if we manage to erase infinity from both black holes and the Big Bang, what does that leave us with? Let's take a look at how this one simple idea could totally reimagine our universe. So, the main takeaway here isn't just that we fixed one little problem. This is a whole new way of looking at things. It suggests that singularities might just not exist anywhere. It redefines black holes, it redefines the Big Bang, and it even suggests that our most fundamental constants of nature are really just descriptions of the physical limits of the vacuum itself. And maybe the most mind-bending part of all of this is what it means for gravity. In this view, gravity isn't a fundamental force in the way we usually think about it. It's an effect. It's what we feel when the physical medium of space-time gets bent and squeezed. It's not a law of the universe, so much as it is a mechanical property of the vacuum. Which leaves us with one final, awe-inspiring question. If this theory is even close to being right, if space-time is a real physical substance with structure and limits, then what else is hiding out there in the vacuum, just waiting for us to discover it?